We're now going to take a look at a set of algorithms that involve cleaning up or removing data. We're now going to take a look at several different algorithms that solve the same problem, and we're going to see some differences between them. This problem is what we call the data cleanup problem. So here's the simple version of the problem. So let's say I have a set of 10 numbers, and I want to remove, or what we'll say clean up, all of the zeros in our list. So let me just give you an example. Let's say our list is 0, 24, 16, 0, 36, 42, 23, 21, 0, and 27. So what we want to do is we want to get rid of all the zeros. So we have a 0 right here. It's not a good circle. Let's try it one more time. There we go. We have another 0 right here, and we have another one right here. So we want to get rid of all these. So our final list is going to end up being 24, 16, 36, 42, 23, 21, and 27. And then we're going to have an additional variable which we would call legit, and it's going to be the number of legitimate values in this list. So in this case we have 7 legitimate values, so legit is going to store the value 7. The first algorithm we're going to take a look at is called the shuffle left algorithm. And the idea with this is pretty simple. We're going to read the list from left to right, and then every time we encounter a 0 in the list, we're going to remove it from the list. We're going to take it out. Now the way we're going to do that is we're going to take everything left over in the list and copy it one cell to the left. So as soon as we see everything, we're going to take everything left over and move it over one spot to the left. And then we're going to take the value of legit, which will initially be the size of our list, and we're going to reduce it by 1 every time we read a 0. Let's do an example of this algorithm. So here we have 10 values. So the value of legit is going to be initially 10. And I have an arrow pointing to the first cell. And as we go through the entire list, we're just going to kind of move the arrow over one spot as we go through here. But right now we're looking at just the first number. And notice that this first number happens to be a 0. So what this means is the value of legit is going to be reduced by 1, and then all the items to the right of the 0 must be copied one cell to the left. So this is what happens after we do one copy, the first such copy. So we move the 24 from the second spot and copy it to the first spot. After the second copy, this is what we would get, where we would take the 16 from the third spot and we copy it to the second spot. We repeat this again by copying the 0 in the fourth spot and moving it to the third spot. We'll then repeat the copying, so we'll copy the 36 from the fifth spot and copy it over to the fourth spot. And if we do the remaining copies for the rest of the list, this is the result we're going to get. So we just copy the 42 to 23 to 21 to 0, all the way down to the end where we copy the last 27 and put it into the spot before that. So this is going to be the result after copying all of the items over by one spot to the left. Since we got to the end of the list, we're going to start over, but now we're going to move our arrow to the second spot of the list and then just start scanning there to see if we find any zeros and copying stuff over. Since the second item in the list was not 0, we can just move our arrow over to the next spot. There's no point in going all the way down. So we'll just move to the next spot and then repeat the whole process. So here we do see that we get a 0, which means we're going to have to copy everything from the right side of this 0 all the way to the left by one spot. So to save time, I don't think it's necessary to do one spot at a time. So this is the result after copying all the items over by one spot to the left. So notice here we now have 27 in 3 different places, and that's okay just based on how this works. And notice that we also reduced the value of legit by 1. We now restart again, and before we were looking at the third spot, so now we're going to move our arrow over to the fourth spot to see if we get a 0. And in this case we don't. It's a 42. So we're just going to keep going down the list and keep moving the arrow over until we do encounter a 0. And we find that we don't find a 0 until we get to the 7th spot in the list. So then what's going to happen is that we would copy everything from the right over by one spot to the left. So just like before, we're going to copy everything from the right side over to the left by 1. So we're going to copy the 27 from the 8th spot, put it into the 7th spot, and then we would reset, and we would move the arrow over one more spot. So this would put us at the 8th spot. So we would be right here. If I can get a good arrow drawing. There we go, that's close enough. And we would also reduce the value of legit by 7. Now notice that we're at the 8th spot, but the number of legitimate values is 7. That means from this point onward, we don't really have any more legit values. We don't need to check for zeros, so we can say that we're done with the checking for any more zeros. Here's the formal pseudocode for our left shuffle algorithm. So we first need to get the value of n and the data items themselves. We need to set the value of legit, and we're going to initialize it to the number of items in the list. And then we're going to have two other values, which we call left and right. Left is going to correspond to where our arrow was in our example. So we're going to initialize that to 1. We're going to have a second value called right, and we're going to initialize it to 2. We didn't actually show this in our example, but the idea with this is whenever we do encounter a 0, we're going to use the right value to go down to the rest of the list to copy things over to the previous slot. So while left is less than or equal to legit, which means that we haven't gone past the number of legitimate items in our list yet, we're going to repeat steps 6 through 14. So we first check to see if the item at position left is 0 or not. If it's not 0, then we'll do step 7 and 8, which is to increase left and right by 1. So we just move on to the next item in the list. Now, if the item at the position left is 0, then we're going to do steps 10 through 14. We're first going to reduce the value of legit by 1, and then we're just going to go down to the rest of the list. So while right is less than or equal to n, we're going to copy the item at position right and store it in position right minus 1, and then we're going to increase right by 1 to move on to the next spot. And then after all that's done, we're going to set the value of right to left plus 1. So wherever left is, we're going to reset right to one position to the right of left. Let's analyze our algorithm. So what we're doing here is we're going to look at each of the n items in the list. Now, if an item is 0, we're going to shift the remaining items. So the first question we should ask is, what's the worst case scenario? So think about that for just a second. Pause the video if you need to. The worst case scenario is that each item is going to be 0. That means we need to do a whole bunch of shifting. In fact, that means we have to shift n minus 1 times to reduce legit by 1. And so we'll do that. We'll do all the shifting over, but the first item is still 0, which means we're going to have to shift all n minus 1 items again. And we got to keep repeating this until legit becomes 0. This means the total number of shifts is going to be n times the quantity of n minus 1, which comes out to n squared minus n. Now, just from what we did before in previous examples, n squared minus n means that this n squared is the dominating part of the total amount of work done, which means this is going to take theta of n squared time. So time-wise, this isn't all that great. It takes theta of n squared. Now, what about the space? Well, it's space efficient because we only need enough memory to store the value of n, the value of left, the value of right, and legit. So we only need 4 memory locations in order to store these values.